everybody. Welcome back to another episode of the Skeleton Crew. I'm your host, Jen Callahan. And today I have a guest with me. His name is Camilo Buscaron, and he is the founder of a company out there called ALAFIA. And they're doing some great stuff out there with, I've never heard of this, but it's called omics computing solutions. So this is going to be news for you and news for me, myself, and learning about something new, like I just said. So I'm going to let Cam go ahead, take the ball. And then Cam, tell us about ALAFIA, and then maybe give us a little background of yourself and how you have ventured into your new company.
Thank you, Jen. Pleasure to be here with you today. I think it's great that you mentioned the omics computing part, because that's something that I think biologists, for the most part, understand what omics is, which is the essential live data that comes out of all the types of biological samples that you can get. Sort of the broad term, but then it can be proteomics, glycomics. There's a whole field of omics, computational or biological analysis. And when we introduce the term computing, what we mean by that is, we believe that we can adapt the computational data structures and the computational technology that we use in a regular computer to be better suited for the biological processes and the biological, ultimately the data structures, how we would encode that in a computer that comes from that technology. So thank you for bringing that part up. And then a bit about me. I spent about 15 years building robotics technology. Most of my career has actually been building robotics technology. I got to work in some great startups and major corporations in Silicon Valley that were developing mostly computational technology for autonomous vehicles. So we're building computers, high-performance computers for autonomous vehicles. We're building APIs for robotic simulations, and we're building robots themselves. And we ultimately ended up building ALAFIA because we had developed some computer vision technology that was becoming very popular among medical imaging researchers. We had this technology that we developed as general purpose, and there was quite a bit of number of medical imaging researchers using our technology, publishing papers how they were using it. And one thing led to the next. We ended up at a hospital network, and they wanted to build an application using the library we had created. And when we walked in there, we realized their problem wasn't that they needed AI. They had just underinvested in their infrastructure. So that led us to building the products that we're launching this summer.
Okay. So let's talk about a little bit of the different products. I'll let you go through them and name them, because some of them have a bunch of different, a bunch of different numbers and some letters attached to them. And maybe you could give more insight as to why they're named that way, and then maybe if it correlates to what it possibly does. But I know that I saw at least 2, possibly 3 of the different products that you have coming out.
Yeah, so the main product that we're building is a platform for precision medicine. It's ultimately an all-in-one high-performance computer, but we have optimized every layer of the software stack to perform at a significant higher level bar than you would with a regular computer. So we've taken sort of the most powerful compute you can find in the world today, sort of off the shelf. We have integrated into our system, and then we have optimized every layer of the software stack, from the kernel to the operating system, to the device drivers, to the middleware. And normally, what we do with our customers, they typically have a scientific pipeline. It could be a neurology research pipeline. It could be a computational biology pipeline, and somehow it doesn't perform great in the existing systems that they could buy. So what we do is we help them optimize that software to leverage the hardware architecture and perform the best that it can perform in any environment. So a lot of our customer engagements today involve very hands-on development with our customers to make their software highly more performant, leveraging our architecture.
Okay. Now, is it possibly because their software that they have is older and like, this is kind of just given a little bump, or is it because it's just completely lacking something?
It's a mix. It's usually a mix of things. So researchers typically are not software engineers, so they don't develop optimized software from the beginning. So that's usually one setback. Other areas could be that they're not as familiar with high performance computing and how you can integrate, how you can leverage computational elements. Um, sort of matrix, let's say matrix multiplication intrinsics, or something, or an instruction called SIMD, single instruction, multiple data. This is a well-known computational element for supercomputing, but medical researchers may not be familiar with sort of the computing, the edge computing capabilities that you could leverage in a high performance system. So, helping them become aware of that and making their data structures more SIMD friendly, then being able to vectorize those computations adds a significant speed up. We also have scale out computational capability. So if they have a piece of software that can be multi-threaded, we have our systems go from 128 cores to 256 cores, so they can leverage that compute in sort of an optimized software stack. They're able to gain a significant advantage that they wouldn't from a normal system.
All right. And are you like hooking this up like directly to, say, like a CAT scan machine, like their like processing station, like, or control station, I guess I should say, or like the X-ray control station, or is it something that's more on the back end of where the radiologists are reading?
Yeah, so this is more on the radiology reading side or on the pathologist side. Getting data from a CAT scan usually would happen through a packed system, right? So the data goes from the scanning systems through a pack, and then we receive that data, and then we can process that data. So if there are applications that are cutting edge and need to run AI algorithms, we're very good at that. We can run that very well. Another perfect example that it's rarely available that we're working with some customers on is digital pathology. So digital pathology, traditionally, when a pathologist would look at a tissue sample or a blood sample, they would put it on their microscope and analyze it. Well, that doesn't happen anymore, right? Today there are this big scanner machines, multi-million-dollar scanner machines, similar to a CT or a PET scan.
Mm-hmm.
And they, the pathologist would put the tissue or the blood sample, it would get scanned by the machine, and that output of that machine is a very large image file. And then
This episode is brought to you by xraytech.org, the rad tech career resource. If you're considering a career in radiology, check out xraytech.org to get honest information on schools, degree options, career paths, and salaries.
One of the differences between pathology and radiology is that pathologists can't really read the way a radiologist would a scan. You actually need to be able to run more tools to classify cells, count the number of cells, to see if there's any elements of cancer, or being able to quantify how spread out cancer cells may be. So they use a piece of software that does a lot of pre-processing. Some of these workloads are things that run overnight that take multiple hours. So where we add value is accelerating these workloads. And typical workloads, that would take maybe 30 minutes or 40 minutes in a regular computer. Today we can do them under 30 seconds. So it's different than a radiology looking at a lesion, in a scan. But I think, with the advent of AI, you'll have more tools in radiology.
Mm-hmm.
Do like long nodules and long nodules detection. Those are very hard things for a radiologist to do. that could be easily missed, right? Because in 400 frames, you may have 3 or 4 frames that show you a long nodule. That's where somewhere where an AI, an artificial intelligence application could help in our system would be relatively supportive, to support that type of applications.
Oh, well, sure, because it can sort through it easier than radiologists, right? Now, is it best utilized for certain types of scans more so than others?
It all depends on the applications that our customers are looking to process. Like I said earlier, it's really just a very powerful computer, probably the most powerful computer you could buy in the world. Then it's a matter of what software applications do they use today, and if there are some limitations. Typically, the customers that we engage on, they're not very happy with the existing systems that they have available to run some of these workloads.
Now, is this something that the scans are automatically run through, or is it something that the radiologist has to choose for it to go through?
Right. So typically with a PACS system, we don't dictate which PACS our customers should use. But PACS systems have different features on how they prioritize readings, right? And what case goes to a radiologist.
Right.
That's all depending on sort of the PACS that our customers will be using. But in cardiology use cases, there are great tools for that, and those tools actually in sort of for cardiology use cases do run a lot of computations to measure flow of blood, not just imaging, but actually running computations to calculate flow and other elements of cardiological analysis.
Now, I was looking on your website and I saw there was many different images of body parts from scans that look very different than, say, images that I've seen from scans. I don't know if you have anything you might possibly be able to share for those who are watching us on YouTube, but there was one of a cross section of the heart, but the image of the heart itself was very different than probably it would actually be seen on a CAT scan. Is that something that I'm assuming that this technology is doing, that transforming the way that it's viewed?
Yeah, so there is one major use case that we support with a number of customers, which is reconstruction. The way reconstruction happens, and this could be, let's say there's cortical reconstruction, so let's say reconstructions from MRI images of the brain or fMRI images, where you have 2D images, you have maybe 400 or 500 2D image slices, and then there's a piece of software that is used to reconstruct those 2D images and being able to create a 3D mesh of the organ. So this is very common in neurology research for cortical reconstruction. Tomography is another area where you also have to be able to reconstruct the images, and then there's a number of software tools. Those type of workloads are heavily computational intensive. They take a significant number of algorithms to pre-process and compute that reconstruction as accurate as possible from the 2D images. Those are the elements that you were seeing on the website. They're 3D images generated from 2D scans.
Okay, cool.
And that is somewhere where the field is moving towards even standardizing, how this data comes off the machines. We've supported a number of researchers, sort of pioneering sort of this collaborative effort to standardize how the data formats and the images come out of tomography systems to be able to reconstruct them. Sort of what DICON did for radiology as a standard format for viewing. There are now efforts to standardize tomography data to be able to reconstruct that data and look at it as 3D
okay.
3D meshes of an organ or a scan.
Okay. So, I mean, obviously, this is very intricate stuff that you're doing. Have you met challenges along the way while developing your different softwares?
Yeah, significant number of efforts to be able to get every aspect of the pipeline working, right? One of them has been developing the hardware technology that can perform this workloads, right? That can run these workloads. So that has been an effort we have been on pursuing for about a year, and we're starting to ship our hardware technology now, our product. And then there's significant software software migration for existing applications, because we sort of have a new microarchitecture that's part of our strategy into being able to create a powerful computer at the form factor and power envelope that we have. We have a microarchitecture that traditional computers haven't really used. So there's a significant effort. Depending on what the application is, there's an effort to migrate that software to fit our microarchitecture. But by doing so, then we leverage the additional compute, and we're able to increase the performance of the application. So that is the benefit, right? There's some level of work involved, but once we do that, then we're able to gain significant advantage on behalf of our customers. Ultimately, right? Most of the applications that we migrate for our customers are all depending on the use cases that they have a need.
Do you have this currently integrated into a fair amount of health systems?
Not quite health systems per se. Most of our customers today are actually in the research side.
Okay.
We have a number. We do have clinics. We have a number of clinics performing neurology research. We have a research center associated with Massachusetts, with Mass General, right? So that per se, but it's mostly on the research side for different use cases that involve neurology research, like transcranial magnetic stimulation, where they use a lot of computation to figure out how to place the coils to stimulate the brain.
Okay.
For cases like depression, obsessive compulsive disorders, that has found significant improvements there because there's as opposed to a pharmacological approach, there are limited side effects. So a number of more research most of our customers today are really bioinformaticians. They are sort of the healthcare application developers, right? They're figuring out what solutions to provide to physicians. And what they're learning, what they like about our system is that, they develop their solution in our system. Then our system is also something that can be on the desk side of a doctor, as opposed to being able to, creating something that would run in the cloud, over a long period of time. Our system, can be a distribution method for them to deploy their application. So mostly bioinformaticians, that sort of use cases.
Yeah, and I saw that you mentioned Mass General, Massachusetts General, for those that are listening. And then I also too saw that you are partnering with Shriners, I guess, again, for the research aspect of it.
Correct. So Shriners is completely focused on orthopedics, right?
Okay.
So that's an element where 3D reconstruction, 3D applications that need to manipulate 3D orthopedic solutions, right? Like a knee joint, or you want to simulate how a knee would behave under different materials. If you use a different support material, those are very 3D heavy. Graphical, have significant graphical elements that are used to our system for visualization, because we sort of have a great sort of interactive 4K screen. All those graphical elements of that are 3D structures that need to visualize, simulated, are use case that we fit a solution very well for.
All right. So obviously you got a lot going on here, in terms of the research world, and you've developed some great products. Where do you see yourself heading in the future with the company? Do you guys have something on the, like, in the works that you're hoping to launch along with the other products?
Yeah, we're very excited to continue to develop the solutions for bioinformaticians. We're partnering with the International Society for Computational Biology.
Okay.
This is mostly around intelligent systems for computational biology, mostly to educate, the next generation of biologists, because now biology has become a field where, it's not just a science that you study; it's actually an engineering field where you can create and create tools and create experiments that are very valuable. So. Ultimately, they are the developers that are going to make the applications for the doctors. So, we hope to provide them with the tools that helps accelerate their discoveries and research. So, we'll be very happy that some major breakthroughs just happen in our system. That's sort of our goal and our vision.
Yeah, doing great things. Everybody, today, this is Cam Buscaron with me talking about the omics computer solutions that they're offering out there in the medical world. So Cam, thanks for taking the time to be with me today and sharing everything that your company is doing. Looking forward to hearing about, the new developments that you'll have coming out in the future. So everybody, Jen Callahan and Cam, this week with the Skeleton Crew, you can check us out on YouTube, Apple Podcasts, and Spotify. So thanks for being with us today. Cam, thanks again for your time. I appreciate it.
Thank you, Jen. Thank you, folks. Have a great day.
All right. See you, everybody.
You've been watching The Skeleton Crew, brought to you by xraytech.org. On the next episode, join us to explore the present and the future of the rad tech career in the field of radiology.